Today's guests are Christina Fernandez-Valle and Bob Hoekstra. We join their conversation in the faculty lounge.
While we burn all the fuel and build extremely high pressures in it, and then accelerate the piston down in a way as fast as we possibly can, because it's going to improve the emissions and the efficiency of the engine. And this new engine design allows us to change the profile, so we can actually control the piston profile. We can have it come up as fast as we want. We can get it to dwell for as long as we want at the top, and we can control how fast the piston falls away. And so now we're back in basic research. Now that we can do this, what's the ideal profile? We don't know, because we've never experimented with these kind of variabilities in the profile.
So is the piston going to be totally different design?
The piston isn't a different design, but the engine itself is, because we have the cylinders are aligned in a circle around the block, and then the whole thing rotates, kind of like a revolver. So the whole engine block is spinning.
So you imagine a pistol revolver, and that's the new design?
Yeah, in the revolver. You imagine that the revolver part of a pistol going around, and the bullets are like the pistons in there, and so the whole thing is rotating.
And then that is anchored to the car frame?
Through a central shaft. You have a central shaft that goes through that, and that gets anchored to the frame. And now, because the block is rotating, we can take the rotary motion off from the block through a gear train.
And that's actually research is going on in your lab right now?
Research is going on in this right now. We're still in, we haven't built a prototype yet. Everything is being done in computer modeling right now. And there are lots and lots of problems to solve. And we can solve those in modeling before we invest in the hardware. To build one of these engines is going to cost about $10 million for the original prototype, for the first off prototype on this. So before we start throwing millions of dollars at building a prototype on this thing, we want to solve as many of the problems as we can with computer modeling. So we're doing the modeling right now, and we're hoping to start building the engine in about a year.
Oh, that's pretty quick.
Yeah, we've been at this now about 5 years now on this. So we've made some of the incremental steps now that we have to.
And then even if you model it with computers, there's always reality, right? When you actually start to build it, you always run into more problems that even the computers hadn't predicted?
There is no question that the first one we build is going to blow up.
Okay.
It won't work. Something's going to break, and we're going to scatter parts around the dyno room, and we're going to have to do it over again. So there's no question it's not going to work the first time.
And this design was first invented or patented in 1901, and then it's been a revival or a renewed interest in it?
1901, and then there were several more that came out, and they actually built these engines and used them in some airplanes, and it didn't work out too good, because in the airplanes you had this rotating mass that wanted to flip the airplane upside down. So there were a lot of planes that crashed, and so they gave up on this design that they call a barrel engine. And nobody ever looked at it again. And the sculptor just thought it was a neat idea to use this thing that was rotating this way. And when it was initially proposed to me, I said, this is crazy. And then started looking at what the differences were. And when we finally understood that we could vary the way that the piston motion inside the cylinder using this kind of design, it really is just exciting research.
And you think it's going to help the efficiency of our fuel consumption long term?
Right now, in a gasoline engine, the standard efficiency is between 27 and 30%.
Oh, that's terrible.
It is and it isn't. I mean, on the one hand, it's absolutely terrible. On the other hand, the theoretical best that we could possibly ever get out of any engine, because of entropy and the heat that we cannot recover, there's no way that you can recover, is about 55%.
Oh, so
we're at about, on that basis, we're at about a 50% efficiency against the theoretical best that we can ever get to. We can never get to 100%. That's impossible. This engine is looking like it's going to be about 44% efficient. We're going to be 3/4 or better
of your maximum
to the very best that we can get with this engine design, and that's why it's so exciting. It has the idea of an entire engine block rotating inside your car is not a great idea, but we think we can manage it.
Yeah, I think of the centrifuges I work with in the lab, and if you have the rotor placed and you have a test tube, we have barrels that hold test tubes. If any one of those aren't balanced and you get these, this high spinning centrifuge going, in the old days before they had emergency stops on them, the rotor would just fly right out of the centrifuge, and it was one of the most dangerous pieces of equipment, that and an autoclave, that we ever worked with in a lab.
Yeah, well, first of all, we're going to keep these at relatively low RPM. The design models we're working with have them at about 3,000 RPM, whereas many engines now are running in 6,000 to 7,000 RPM range on it. So it's going to be a lower RPM engine. The other thing is that it won't accelerate. This is going to be a constant speed engine because the engine block itself is a flywheel. And so initially getting this thing going, bringing that flywheel, that engine block up to speed is going to take a long time. So it's the vision for this is that it's the perfect engine for a hybrid vehicle.
So you're going to have the electrical engine that takes over during the acceleration phase, and then you have the barrel engine, which takes over for long-term cruising, or?
That's one model. One model is the one that you've exactly described. The other model is where the engine drives a generator and the car always runs on the electric motor.
I see.
And so the question is, do you ever take the power directly off from the engine itself, or do you share responsibilities? The hybrid vehicles that we have today right now, all of them share responsibility.
And that brings us to fuel, alternative fuels. That's the other area of research that you're involved in.
Yes, and that's a very, very frustrating area to work in, because you finally, after you've studied it enough, you realize that there are no solutions. There's only pieces of solutions. There's no magic bullet. There's nothing that we're going to be able to do that's going to significantly change what we're doing.
Well, so I've heard yesterday on the radio that some kids in Orange County go to school on school buses that are now have a combination fuel, where part of it is type of oil or
biodiesel.
Yeah, biodegradable. Yeah.
Well, it's biodiesel.
Corn oil or
yeah.
What about that?
There are a lot of problems. One of the problems with the biodiesel, which will run in a diesel engine, is that it has no shelf life.
Oh.
Because it's organic, it degrades.
And you get bacteria growing in it, right?
All kinds of things. And so the shelf life of biodiesel is about 6 months, which means that we have just huge infrastructure problems. Because we have to manufacture it, get it to the fueling stations through the distribution system and into vehicles and used before this stuff degrades. Because when it degrades, it plugs up all the filters and shuts the engines down. And in fact, the military has made a decision that until those problems are solved, they will not use any biodiesel at all, because they can't risk having the military shut down because they had the stuff in storage too long. Right.
So with the counties using it for their school buses, where are they having direct shipment, or where do you?
I don't know. It does. There are a number of different emissions that come out of vehicles, and it turns out that the emissions with biodiesel, some of them are much worse and some of them are better. And so the problem with the reports that we get and what the media does is we keep getting told half-truth, and we believe the half-truth as being the whole truth.
Right.
When you really dig into it and find out what the other parts of it are, you find out that there really is no good solution.
Not even hydrogen-fueled cars.
Where do we get it from? You know, the standing joke is, well, the last hydrogen well ran out a few years ago. The truth is there never has been. We have to make it. And so, well, we can take water and crack it, but the amount of energy it takes to break water apart is enormous, and we'd only get back a percentage of it. So where do we get the energy to break it apart? Oh, I don't know, a coal-fired electric plant? I mean, we have to do it, use electrolysis. So let's look at the cradle to grave, this perfect, pure burning hydrogen. We probably caused an enormous amount of pollution, at least greenhouse gases, to make it in the first place. So it's not the magic bullet. And we don't know how to make it efficiently. We have no idea how to store it efficiently. Because if we store it as a cryogenic liquid, in Florida, we lose about 10% of it a day.
That's going to work well.
So we don't know how to transport it. Because if we would go to the hydrogen economy right now, we're going to be hauling this stuff up and down I-4 in cryogenic tanker trucks. And when that tanker truck has an accident, it's bad enough if it's a gasoline and it burns out in a few hours and they put foam on it and get it to stop. Start a hydrogen fire out of a tanker truck that had an accident, and the estimates are now that it would burn for 2 weeks. And
one truck would burn for 2 weeks?
Would burn for 2 weeks, and we have no known technology for putting the fire out. And so you literally shut I-4 down for 2 weeks.
Wow.
And that's one accident. How often are we going to have an accident on I-4 or the 408 or the Turnpike or 95, shutting down the infrastructure in the United States?
And where would you manufacture it?
These are all the questions
can you do local manufacturing, or?
You can do local electrolysis if you can bring enough electricity to bear on it, and our grid is overloaded right now. So we don't have the electrical grid to distribute the energy to the places where we could make it on a local basis.
So the hydrogen-fueled car is really still a bit of science fiction?
Oh, very much science fiction in terms of being able to do it practically. If we can use hydrogen in an internal combustion engine, there are a lot of problems with that, and we gain some efficiency, but it's not all that much better than gasoline. So let's go into the fuel cell technology.
Okay.
The basic cost of a fuel cell is $2,000 per kilowatt, and that's about 1.25 horsepower. So by the
that's not much. We're not going very fast at that speed.
No, and we need to have at least 100 kilowatts. And so you start adding up the cost of a fuel cell vehicle plus the electric motor, the fuel cell, all of the other things that have to go into that vehicle. The going price right now is about $1.5 million for a vehicle. And they say, well, yeah, but they're not in mass production. In mass production, the best estimates are right now that a car would cost $250,000. Well, that's not a solution. And we still don't know where we're going to get the hydrogen to make it run.
Right. So maybe the best model is just the smaller cars, like the European drives, because they have small roads. We have to get rid of the large, suburban type vehicles. Maybe
the best model is hybrid vehicles with some new engines. The engine that we were talking about a little earlier is a possibility. I've done a lot of research in hydrogen methane mixtures, natural gas and hydrogen, running in an internal combustion engine. And we get some really good efficiencies out of that and low pollution. The only pollution that we have to differentiate between pollutions too. Do we consider CO2 a pollutant? If we do, because we're concerned about greenhouse gases, then we're at the end of the road. There's nothing we can do. Because everything's going to be hydrocarbon based, and where is the carbon going to go?
Right.
It's going to become CO2. And so the only thing we can do is try and use it as efficiently as we possibly can. But we're going to make literally tons of CO2 to transport us around. And that's true whether we're running hydrogen or not. The easiest place to get hydrogen is by cracking methane. So you get some hydrogen off, but you also get the CO2.
Methane, CH2.
No, CH4.
CH4. Yeah.
Yeah,
For
so
my
you get
chemistry days.
four atoms off, but you still have that carbon molecule. And that's the very best that we can do, because any of the other chains have more carbons in them, and we're actually losing ground.
Right. So you're excited about your barrel engine, and you're excited about methane as a source.
Because we can make it.
So that's more realistic.
It's a lot more realistic. It's just not in favor right now. It's a lot
It has to come
sexier
around.
to talk about pure hydrogen vehicles, and that's what I find so frustrating. I spoke at a conference not that long ago, and the title of my speech was The Great Hydrogen Lie, and in a half hour laid out each one of the lies, some of which we've been talking about. You know, it doesn't pollute. Well, yeah, but it does on a cradle-to-grave basis.
Right.
Let's be honest.
The
about it.
consumer doesn't pollute, but the manufacturer polluted.
They have to. They're going to be either through the use of the electricity. I mean, it's not going to come from solar cells. It takes way too much energy. We were doing work at the Florida Solar Energy Center. This was about 10 years ago with solar cells. And we had $1 million array, and we were able to make enough hydrogen to power a vehicle to go 50 miles a day.
I think we need to restructure our communities, right? So that we work out of our homes, or our offices, or school, are all within the same large development, which has been a change. You know, the new communities everything is within walking distance. You no longer have to commute, right?
That sounds like the old communities,
Right.
because when you were riding horseback, you could go 5 miles a day and that's it. You know, so yeah, I mean, as long as we continue to do what we're doing, we're going to get the same results. And what is so frustrating is that the politicians don't want that said.
Paint the rosy picture.
It's going to be okay. Hydrogen's just around the corner, and everything will be fine. It's not.
And when you really stop and talk to the experts and find out how far we have yet to come and what are all the obstacles we have to, solve before we get there, you're not being a pessimist, you're being a realist.
Well, and I believe that the problems are solvable.
But you think...
But no money's being invested in the research.
You need the basic research.
The basic research is not being done.
Yeah.
All the money is going into demonstration projects. And we're demonstrating what we know, and what we know won't work.
Won't work. Well, it's kind of the same thing in my field. I was trained as a basic scientist, and my philosophy is, if I don't know how a cell works, how can I fix a sick cell? If you don't know how an engine works, how can you improve on the engine? So you spend some time studying the basics, and from the basic knowledge, you end up with new information. But right now, the goal of a lot of the research that's funded is to get what we call translational applications. Get a new drug, find a new target for a drug, find a new medicine that's going to help us. And what we find is the basic science isn't funded. It's difficult to get funding from the federal government. And a lot of the basic science, good basic science in my field, is being done in Europe, because they still value the basic science there. And we're still thinking, okay, let's take a product to market. And we all need to think that way, but we still can't forget the value of the basic science, the basic research, because that's where the new information is coming from.
I suspect that if we talk to our colleagues just across fields, we're going to find out that that's exactly where we've ended up in the United States right now, all of the funding branches. Another colleague of mine was doing basic research in housing development to significantly change the way, lost his Department of Energy grant because they want demonstration projects.
Right.
They don't want basic research in new forms of housing.
Yeah, we're all having to reinvent ourselves and say, okay, if I can't get the money doing the basic science, how do I get the money to keep the research going? And you change and you do a demonstration project.
And we can do that, but that doesn't solve the problem.
No,
it doesn't solve the underlying problem. And I don't know what the solution is. I mean, But then that's why we do the research.
Right.
I mean, the fact that we can't write a proposal today and say, here's the solution to the energy problem in the United States shouldn't disallow the research. It should fund the research, the honesty that we don't know, and we're going to go looking at those hard questions. But no one wants to listen to that right now. Just give us the magic pill that will do something that really looks nice and publish the paper and move on. And that's where we are in this whole energy thing right now. There are little reports that come out on like the use of ethanol, and they do a cradle to grave calculation on the amount of energy it takes to make ethanol and what pollutants are created in the process of making that ethanol. We're way behind using gasoline.
Oh.
When you start
surprising.
looking at the amount of energy that the farmer uses in the process of growing it and harvesting it, and then the energy
corn,
that is
right?
on the corn
Yeah.
and go through the whole process, it's not very good. It's not very good. And then we end up with some really unfortunate pollution as a result of the ethanol too. All the aldehydes that it produces when it burns.
Yeah, aldehydes are really nasty chemicals, aren't they?
Really nasty chemicals.
Yeah, I use them in the lab. You fix things. I mean, a little bit of aldehyde is very toxic to a cell. I can only imagine if you start breathing air that's contaminated with aldehyde fumes.
And it's not a regulated pollutant at this point. So everyone can talk about how efficient these new vehicles are, and they don't pollute as much because we don't measure that pollution. As long as we ignore it, we're fine.
I mean, indoor pollution, a lot of the new home construction, if you don't watch the kind of quality of the wood construction that you use in the cabinets, they're all outgassing formaldehyde.
Yeah.
There are a number of people that are very sensitive to indoor pollution, and they get asthmatic, they get weak, they're fatigued, and it's the quality of the indoor air, which is, you know, the glues we use to hold the particle board cabinet together is off-gassing formaldehyde vapors.
Yeah.
That's a whole movement toward green construction,
Yeah.
which is also healthier, not only for the environment, for individuals as well.
But now we're going to be dumping all those aldehydes into the environment out of our tailpipes.
Yeah. So there's something else fun that you do in your line of research. Do you want to talk about that
Well, it's not research, but a fun thing I do is build racing engines, because if we can't solve the world's problems, at least we can play.
Right.
And that's how I regard racing. Has no socially redeeming value other than it's fun.
It's fun, and people need to have a way to unwind and relax from the stress of life, and to go to the Daytona and watch the cars zip around. And you make really fast car engines, right?
We try. I mean, that's our goal, is to make an engine that produces more horsepower than anybody else's. And when we're doing that, pollution is the least of our concerns. That's just about making power.
See, so you're very well balanced. I mean, on one end you're polluting, at the other end you're really focused on, you know, fixing that problem. So what is the fastest engine you've built, or your affiliation with the race team?
Well, the most of the work I've done is on an engine, the small block Chevy, the venerable small block Chevy that was actually initially designed in 1953 and has remained virtually unchanged, very minor changes over all these years. In the 60s, 70s, they used a lot of the small block Chevys in cars, and they made about 180 horsepower. And we take that same engine and just do a few minor modifications, rub on it a little bit, and we make 850.
From 150 to 850?
Yes.
Well, what did you rub on it?
we change the way that we get air into them. So if you can get enough air into an engine, you can always get enough fuel in. And the air and fuel have to be in exactly the right proportion. If we can find ways to get more air in, we can always add the fuel in, and the more air and fuel we get in there, the more horsepower we're going to make. But along the way, we've learned lots of things that actually have some socially redeeming values. Over the last 5 years or so, the biggest gains that we've made on racing engines has been reducing friction. And that technology is going directly into the vehicles that we're driving today. And that's how engines are going from 20 miles to the gallon up to 30 miles to the gallon, is because we're finding ways to reduce the friction in the engines that we currently have.
Those are just the new synthetic oils that are made, or?
No, it's gone so much further than that. We've found the size of the piston rings. The biggest loss is the friction of the piston moving up and down in the cylinder. There's a lot of friction in there, and most of that comes from the piston rings that seal it up. You have to have those rings in there to keep those gases sealed at the top and actually drive that piston down. We're making those rings smaller and smaller and smaller, and because of better manufacturing techniques, they still seal just as well, but the friction has dropped tremendously.
So they're small.